Hello, I'm Fei Gui, a PhD student from Tsinghua University. Today, I'm excited to present our work on employing multi-experience parallel simulation to accelerate design space exploration for LLM training systems. This represents a collaborative effort with Zhongguancun Library and the University of Pennsylvania. Now, let me begin by setting the context. Analysts forecast that the LLM training infrastructure market will reach more than $200 billion by 2030, with a compound annual growth rate of 25.5%. And these leading tech companies are ramping up their investment. To justify the investment, we need to explore various design options. For example, during the planning phase, we would ask what the most suitable interconnection topology for our GPU scale. During operations, what hyperparameter should we use for training? The procedure can be defined as the design space exploration. We have many ways to do this job. Among all validation tools, hello testing is costly and inflexible, while emulators also come with high expenses. Therefore, ISO low-cost and flexible alternative, simulators are the best choice. However, the scale of model LLM training clusters is huge. Industry leaders are building superclusters with hundreds of thousands of GPUs, creating extremely wide and deep design space, and the design optimizations at different levels are highly complex and interrelated, which causes that massive simulations experiments are required to find the optimal configurations. For example, 100 experiments just for parallelism strategies, up to 10,000 experiments for optimal topology. But our insight is that these experiments are embarrassingly parallel, which brings us to our key question: how can we execute them most efficiently? However, existing simulators are not optimized for the execution of embarrassingly parallel experiments. For example, in some simulators, such as N3, single experiment is accelerated by a single process with multi-thread. And N3 also supports that single experiment is accelerated by multi-process, but with high synchronization overhead. And for N3, multi-experiments also can be accelerated by a single process with multi-thread, which can avoid the context switching cost and high synchronization overhead. Also, N3 can support that the multi-experiments are accelerated by multi-process, but at high cache miss rate. Further, we first propose categorizing parallel strategies along two axes. One, single process versus multiple process. Should we use a single process or multiple process to accelerate a single program? Two, single experiment versus multiple experiments. Should we execute one independent experiment or multiple independent experiments with one single program? As a result, we can get 4 parallel strategies. And we implemented those 4 parallel strategies to compare them. The scenario involved searching for the optimal collective communication algorithm for a cluster with 128 GPUs, training a GPT-3 30 billion parameter model. And we measured the time to require to complete 1 to 500 independent simulation experiments on CPU server and cache miss rate. The results show that first, MP multi-process exhibited the poorest performance due to high synchronization overhead. It requires 2,000 hours to complete 500 independent experiments. Meanwhile, SPME, single process, single experiments, performs poorly because it has high cache miss rates caused by context switching among experiments. Most important, SPME, single process, multi-experiment, performs best because it's more cache-friendly, but it still requires over 370 hours to finish all the experiments. So how to unleash the potential of SPME? To answer the question, we propose Multiverse, the first GPU-based LLM training simulators, which is also based on the SPME and the DoD. First, DoD enables parallel execution of identical simulation logic across experiments. We can exploit parallel opportunities of SPME across experiments. Second, SPME and DoD execution model aligns perfectly with GPU's SMD single instruction multi-data capabilities. Third, GPU massive cores and SMD optimizations offer significant performance advantage for SPME. The next is architecture. Multiverse is composed of 4 key components. User input supports chakra form. System simulator control and schedule the process of AI training. Inter-server communication simulators execute the analytical model with different empirical parameters according to the operator type and the GPU type. And inter-server network simulator conducts packet-level discrete event simulator for cross-network communication. All components run on the GPU using the SPME execution model. The following is the workflow of Multiverse. The system simulator takes the model workload, parameters, and configurations as input and iterates through each operator. For computation operators, it updates the simulation time based on annotated computation times. For inter-server computation operators, it uses the analytical model to simulate. For inter-server communication, it ingests point-to-point demands into the network simulators for discrete event simulation. However, we face 3 challenges. First, how to model the SPME to employ the parallelism across experiments. To address that, we employ DoD modeling for LLM training and column storage management across experiments. In the modeling for LLM training, there exists different kind of entities which is responsible for different kind of data parallel computation at its simulation logicals. Finally, the system's execution graph defines the execution order and the dependency of systems. As for column storage management across experiments, the data of multi-experiments is stored as a centralized table. And the data of one kind of same entities from different experiments is stored contiguously in memory. The second challenge is how to execute DoD efficiently in GPU. To address that, we designed a pool-based and the kernel fusion technique to address that. As we know, GPU next of lock-free synchronization mechanisms in the many to one write conflict scenario, such as multiple to one forwarding in egress ports in a network switch. And the overhead of GPU to CPU synchronization is very high, which limits the efficiency of simulation using GPU. So first, we employ the pool-based synchronization technique to enable the lock-free multi-threading. Second, we fuse systems together, reduce the total occurrence and the duration of CPU to GPU communications, which also greatly increase GPU utilization. The third challenge lies in how to guarantee the correctness of the execution order. We propose threading model across experiments to address that. In the threading model, multiverse executes different systems sequentially in the execution graph. And for each system, it uses all GPU cores to process all experiments in parallel and batch. For example, multiverse start from running a schedule system, which integrate overall loads of training workload. Then to run sense system, which runs congestion control algorithm and sends packets into network. Then to run forward systems, which forward packets based on the forwarding table, and then to transmit system, receive system. As for implementation, multiverse is developed by C++20 in addition to GPU execution. Multiverse also supports CPU execution. Multiverse supports the following features, include different parallel strategies, collective communication algorithm, user-defined topology, and congestion control algorithm. And multiverse is under active developing projects. We have already open sourced 2 versions. The next is evaluation. We tested multiverse speed, scalability, accuracy against existing simulators. As for simulation speed, multiverse is 15.7 to 73 times faster than other simulators. And multiverse supports up to 54,000 GPU in single experiments, which is 43 times speed up. As for simulation accuracy, multiverse has less than 3% error compared to real LLM training data. The next is ambulation study. Using the analytical model, multiverse can achieve a speed up of 1.7 to 1.8 times. And we employ pool-based synchronization. Multiverse can achieve a speed up of 3.2 times speed up. Finally, the kernel fusion. With the kernel fusion technique, multiverse can reduce the simulation time by 16.6 to 18.6%. As for analytical model evaluation, results show that the error is merely 0.8 to 1.2%. So let's take a conclusion. Simulation can used to do the design space exploration, which can help justify the investment of LLM training systems. So we built a GPU-based simulator, multiverse, which take single process multi-experiments and design 3 techniques to address some challenges. First, we employ DoD modeling for LLM training and the column storage management across experiments to employ the parallelism across experiments. Second, we designed the pool-based and the kernel fusion technical to execute DoD efficiently in GPU. Third, we propose threading model across experiments to guarantee the correctness of the execution order. In the future, more device and protocol should be supported in the LLM training simulator, and the unified precise simulation of intro and the inter-machine simulations can be useful. And fault tolerance simulation for LLM training systems is also an interesting direction. And our simulator is open sourced. Feel free to use it and contribute. Thank you.